Okay, let's unpack this. Have you ever just, looked up at the night sky and felt completely dwarfed by it all? Asking those huge questions. Where did we come from? How did this whole universe even get here?
And maybe even, how did we get to the point where we could even start asking these things?
Exactly. They're not just idle thoughts, are they? They're the big ones.
Definitely. They've driven human thinking for, well, millennia.
Right.
From the very first sky maps right up to modern physics.
Right. And today we're doing a deep dive into some source material that tackles that journey head on. We're focusing on Stephen Hawking's, iconic book, A Brief History of Time.
Ah, yes. A book that really struck a chord with so many people.
It really did. It tackled these ultimate questions in a way people could actually grapple with. Hawking himself said its success showed just how much people want to understand the universe's origins and structure.
There's deep curiosity there.
So our mission today is basically to guide you through the really key ideas in this material, the breakthroughs, the mind-bending concepts.
From ancient ideas about the cosmos to relativity, quantum mechanics, black holes, all the way to the search for, well, a theory of everything.
We'll try to pull out those aha moments, those surprising connections without getting bogged down in, every single equation.
Sounds like a plan. We'll trace how our picture of the universe changed, the big shifts, the puzzles.
Okay, let's start then. Let's wind the clock back. Not quite to the Big Bang yet, but to where people first started trying to make sense of the cosmos in a structured way.
We're talking ancient Greece, around 340 BC. You've got Aristotle. His ideas, later refined by Ptolemy, gave us the geocentric model.
Earth at the center, not moving, everything else. Sun, moon, stars going around us.
Right. In perfect circles, carried on these invisible crystalline spheres. And the outermost sphere held the fixed stars.
It sort of fit what they saw, but also their philosophy, didn't it? Earth being special, circles being perfect.
Exactly. But what's really impressive is how they used observation, even back then. Aristotle had solid arguments for why the Earth had to be round, not flat.
Oh, yeah. Like, what? I mean, it seems obvious now, but...
Well, he noticed the Earth's shadow on the moon during an eclipse. It was always round.
Ah, right. Only a sphere casts a round shadow no matter how it's turned.
Precisely. A flat disk wouldn't do that consistently. And he also noted the North Star.
How it gets lower in the sky as you travel south.
Yes. The change in angle only makes sense if you're on a curved surface.
And a classic ship on the horizon thing, seeing the sails first.
That too. Simple observations, but really clever deductions. Ptolemy's model, even though wrong, could actually predict planet positions okay for its time. That's why it stuck around for, what, over 1,000 years.
And it fit neatly with religious ideas, too, right? Heaven just beyond the stars.
It did provide a tidy picture, but it got messy. To explain why planets sometimes seem to go backwards, they needed epicycles, circles moving on circles.
Sounds complicated.
It was. It started feeling a bit forced, and that's where the big shifts started. Copernicus saying, maybe the sun's at the center.
But it was Galileo with his telescope who really pushed it, wasn't it?
Absolutely. Seeing Venus go through phases like the moon, seeing moons orbiting Jupiter, that just didn't fit the Earth-centered picture.
And that got him into trouble with the church. Big trouble.
Yeah, trial, house arrest for life. He was even forced to publicly recant, saying the Earth didn't move.
Terrible. But he kept working.
He did. Amazingly, while still under house arrest, he finished his book, Two New Sciences. Got it smuggled out. That book really laid the groundwork for modern physics, studying motion.
Incredible persistence. And then Newton comes along.
Isaac Newton. He took Galileo's work and built this grand structure with his law of universal gravitation.
Suddenly, apples falling and planets orbiting were part of the same system.
Exactly, a unified mathematical system. And he introduced this idea of absolute space and absolute time, a fixed backdrop for everything, with one clock ticking the same for everyone, everywhere.
It's funny, the guy who brought such order was apparently quite difficult. The source mentions feuds like the one with Leibniz over calculus.
Oh, definitely a complex character.
Yeah.
He was even warden of the mint, chasing counterfeiters. But his work was monumental. It established this core idea. The universe follows rational laws we can figure out.
That really set the stage, didn't it? But Newton's perfect clock? That didn't last forever.
Nope. Enter Einstein. The first challenge came from light.
James Clerk Maxwell's work on electromagnetism, right? His equations said light travels at a fixed speed.
Yes, but fixed relative to what? If everything's relative, that's a problem.
People thought there must be this invisible ether filling space that light moved through.
That was the idea. So if Earth is moving through this ether, the speed of light should look different depending on which direction you measure it.
The Michelson-Morley experiment tried to find that difference.
In 1887, yeah. And the shocking result was no difference. The speed of light was the same no matter how Earth was moving. No detectable ether.
Yeah, the ether wasn't real. And the speed of light is constant for everyone. That completely breaks Newtonian intuition.
It does. Speeds don't just add up like you'd expect. This constancy was Einstein's starting point for special relativity in 1905.
And the big takeaway was,
No absolute time. Time is personal. Your clock and my clock can tick at different rates if we're moving relative to each other. Distance becomes relative to...
okay, wait, my clock ticks differently depending on how fast I'm moving. That's deeply weird.
It is. But it's a necessary consequence of the speed of light being constant. And it led to, even see why.
Energy and mass are equivalent, and the cosmic speed limit.
Right. Nothing with mass can reach the speed of light because its mass would become infinite. It would take infinite energy. Only massless things, like photons, travel at light speed.
And this even changed how we define things like the meter.
It did. Distance is now fundamentally linked to time via the constant speed of light. The meter is defined by how far light travels in a tiny fraction of a second. Light speed is baked into our measurements now.
Okay, so time is relative, space is relative, and this led to space-time.
Yes. The idea that space and time aren't separate things, but are woven together into a four-dimensional fabric. An event needs 4 coordinates. 3 for space, 1 for time.
4 dimensions, I always struggle to picture that.
You and me both. It's hard to visualize. Think of it like mapping the Earth's surface that's 2D, needing latitude and longitude. Space-time is 4D. You can choose different coordinate systems that mix up space and time in different ways.
And light cones come from this?
Right. Imagine an event like a flashbulb going off. The light spreads out. In space-time, that spreading sphere forms a cone. The future light cone is everything that can be affected by that flash. The past light cone is everything that could have affected it.
And anything outside the cone is elsewhere, causally disconnected.
Exactly. Because nothing travels faster than light. If the sun vanished right now.
We wouldn't know for 8 minutes, because we're in its elsewhere for that time.
Precisely. And when we see a galaxy billions of light years away, we're seeing its past light cone reaching us now.
Okay, special relativity deals with constant speeds. But gravity. Newton's gravity acted instantly, right? That breaks the speed limit.
Big problem. That's what Einstein tackled with general relativity in 1915. His
Yeah.
amazing insight. Gravity isn't a force.
It's the curvature of space-time itself.
Yeah.
Caused by mass and energy.
You got it. Mass and energy tell space-time how to curve. And curved space-time tells matter how to move. Earth orbits the sun because it's following the straightest possible path, a geodesic, through the curved space-time created by the sun's mass.
So space-time isn't just a stage, it's an active player.
Totally dynamic. It affects matter, and matter affects it.
And there was proof.
Oh yeah. It perfectly explained a tiny wobble in Mercury's orbit that Newton's theory couldn't. And crucially, it predicted light itself should bend when passing massive objects.
Which they saw during solar eclipses. Starlight bending around the sun.
Famously confirmed. It was a revolution in thought.
Just incredible. And the source mentions Einstein's life beyond physics, too.
Yeah, some interesting points. His early pacifism, which he later gave up, facing Nazism. His support for Zionism, even without religious belief.
And the atomic bomb. He urged Roosevelt to start the project.
He signed the letter, yes, fearing Germany would get there first. But then he spent years warning about nuclear war. A very complex figure, deeply engaged with his times.
Okay, so we've moved from a static, Earth-centered view to this dynamic, curved space-time. Where did our cosmic picture go next?
To the idea that the whole universe is expanding, that came from looking at light from distant galaxies.
Using spectroscopy, breaking light down.
Exactly. You can see what elements are in stars, their temperature. But in the 1920s, astronomers noticed the light from most distant galaxies was shifted.
Redshifted, meaning they're moving away from us, like the Doppler effect with sound.
Just like an ambulance siren changing pitch. Redshift means longer wavelength, moving away. Blue shift, shorter wavelength, moving towards.
So most galaxies are moving away.
Yes. And Edwin Hubble found the key pattern. The farther away a galaxy is, the faster it's moving away. This isn't just galaxies flying through space.
It's space itself stretching, carrying them along.
That's the interpretation. And remarkably, someone had predicted this years earlier from Einstein's theory.
Friedman, the Russian mathematician.
Alexander Friedman, yeah.
Yeah.
Back in 1922. He just assumed the universe looks basically the same everywhere and in every direction on large scales anyway.
Homogeneous and isotropic.
Right. Based on just that and general relativity, he showed the universe couldn't be static. It had to be expanding or contracting. Hubble showed it was expanding.
Is that assumption that it looks the same everywhere really true?
Well, obviously not locally. We have stars, galaxies,
Hmm.
but averaged over huge distances. Yeah, it seems remarkably uniform. The big proof came later, though.
The cosmic microwave background? The CMB?
Exactly. Penzias and Wilson, 1965, accidentally find this faint microwave hiss coming from everywhere.
Which turned out to be the leftover heat from the Big Bang, the afterglow.
Precisely. And the fact that it's almost perfectly the same temperature in all directions is stunning confirmation of that large-scale uniformity Friedman assumed.
But not perfectly uniform, right? The COBE satellite found tiny variations.
Tiny, like 1 part in 100,000. But finding them was huge. Those little temperature ripples are seen as the seeds of all structure.
The fingerprints of creation. Tiny density differences in the early universe that gravity then amplified.
That's the idea. Those tiny fluctuations grew into the galaxies and clusters we see today. Their pattern matched predictions beautifully.
Wow. So expansion, CMB, fluctuations, it all points to the hot Big Bang model. Universe starting incredibly hot and dense, then expanding and cooling.
That's the standard model. In the first fraction of a second, a soup of particles and energy. By about 100 seconds, things cooled enough for light elements like helium to form.
Then millions of years later, atoms form.
Right. Electrons join nuclei. And then, thanks to those initial density ripples, gravity starts pulling things together in the slightly denser spots. First stars, then galaxies.
So those tiny CMB ripples are literally why we have galaxies, stars, us.
In a very real sense, yes.
Hmm.
But the Big Bang model, based on GR, has a problem right at the start.
The singularity, infinite density, infinite curvature, where the physics breaks down.
Right. It's where the theory stops working. For a long time, that bothered scientists. Some like the idea of a creation moment beyond physics.
The source mentions the Pope declaring it consistent with the Bible in 51.
Yes, but many scientists felt it was, well, unsatisfactory, like giving up on explaining the very beginning.
Which led to alternatives, like
Yeah.
the steady state theory.
Bondi, Gold, and Hoyle in the 40s. Their idea was matter is continuously created as space expands, so the universe always looks the same on average. No beginning, no end.
An eternal, unchanging universe.
Kind of elegant. But observations didn't back it up. Radio source counts suggested the universe did look different in the past. And the CMB was the killer blow, clear evidence of a much hotter, denser past.
So Big Bang won, but the singularity problem remained.
It did. Then Roger Penrose showed in 65 that collapsing stars must form singularities, black holes.
Using light cones and GR math.
Yes. And then in 1970, Roger and I published a paper extending that.
Applying it to the whole universe.
Right. We showed that given GR and the amount of matter we see, the universe must have started with a singularity, the Big Bang singularity.
Was that controversial?
A bit. Some resistance from the Soviets, maybe for philosophical reasons about determinism. Others just disliked singularities, felt they were sort of ugly parts of GR.
But the math held up.
The theorems became accepted. But they also highlighted something crucial. GR isn't the whole story at the beginning. When things get that dense and hot, you need...
Quantum mechanics, the physics of the very small.
Exactly.
Okay, quantum mechanics starts with Planck. Energy comes in little packets, quanta.
Right. Discrete units, not continuous. Which leads to really weird stuff, like Heisenberg's uncertainty principle in 1926.
Can't know a particle's exact position and exact momentum at the same time. The more you know one, the less you know the other.
That's it. It feels totally wrong intuitively, doesn't it? If I see something, I know where it is and how fast it's going.
Yeah.
But at the quantum level, measuring affects the thing you're measuring. To see a particle's position precisely, you hit it with high-energy light, a quantum packet. But that kick changes its momentum unpredictably.
So does that kill the idea of a perfectly predictable universe? Laplace's demon, knowing everything, calculating the future.
That's a huge implication. Uncertainty introduces a fundamental randomness and unpredictability into physics. Quantum mechanics gives probabilities, not certainties.
And Einstein hated that. God does not play dice.
Famously, yes, even though his own work helped found quantum theory. But despite his objections, QM works incredibly well. It's behind almost all modern tech.
Yeah.
Lasers, computers, chemistry.
Its big problem is fitting with gravity, right?
That's the challenge. But first, what is this quantum world made of?
Electrons, protons, neutrons. For a while.
Yes. Chadwick found the neutron in 32. Fun fact, he later became master of my college at Cambridge, Caius.
Huh. Small world, even in physics history.
Indeed. But then experiments showed protons and neutrons weren't fundamental either. They're made of quarks.
Quarks, named by Murray Gell-Mann from James Joyce.
That's the story. 3 quarks for Mustermark from Finnegan's Wake. Most physicists say it like lark, not quart.
Good to know. So quarks make up protons and neutrons.
Yep. 6 flavors up, down, charm, strange, top, bottom, and 3 colors, red, green, blue. Not actual colors, just labels for how the strong force works.
Like electric charge for electromagnetism?
Sorta. A proton is 2 up quarks and 1 down. A neutron is 2 down and 1 up. Each has 1 quark of each color, making them color neutral overall.
Okay, so we have matter particles like quarks and electrons, and then force particles.
Correct? Classified by spin. Matter particles have spin 12. They obey Pauli's exclusion principle.
No 2 identical particles in the same state, same place, same velocity.
Right. That's absolutely crucial. It's why matter isn't just squishy, why atoms take up space. It's electron exclusion that holds up white dwarf stars, neutron exclusion that holds up neutron stars.
And force particles.
Integer spin, 0, 1, or 2. They don't obey exclusion. In quantum theory, forces happen when matter particles exchange these force carriers.
One particle emits a force particle, recoils, another absorbs it, changes motion.
Kind of like throwing a ball back and forth. These exchange particles are usually virtual. They pop into existence just long enough to do their job, but they mediate the force.
And sometimes they can be real particles.
Yes. Real photons are light waves. Real gravitons would be gravitational waves.
Okay, so these exchanges give us the 4 fundamental forces.
Which we really think are just aspects of one deeper force, but yeah, currently 4.
Gravity first.
Carried by the spin 2 graviton, felt by everything with mass energy. Weakest by far, but always attractive in long range, so it dominates large scales. Planets, stars, galaxies.
In electromagnetism.
Carried by the spin 1 photon. Acts on charged particles. Hugely stronger than gravity-like, ridiculously stronger.
So why doesn't it run the universe?
Because charges come in positive and negative. They cancel out on large scales. Planets, people, were electrically neutral overall. But for atoms and molecules, electromagnetism is king, holding electrons in orbit, binding atoms.
Okay. Third is the weak nuclear force.
Spin 1 W and Z bosons. Very short range. Responsible for radioactivity, certain particle decays.
And finally, the strong nuclear force.
Carried by the spin 1 gluon. Acts on quarks and gluons, the strongest force, but super short range, basically inside protons and neutrons and holding the nucleus together.
What does it do exactly?
Binds quarks into protons and neutrons. And holds protons and neutrons together in the nucleus, fighting off the electric repulsion between protons. It has this weird property called confinement.
Can't get a quark by itself.
Never. They only exist in these color-neutral bundles. Try to pull them apart, and the force gets stronger, eventually creating new quark-antiquark pairs.
Seems hard to study then.
But they also have asymptotic freedom. At really high energies, like in particle colliders, the strong force gets weaker. The quarks inside protons almost act like free particles for a split second.
Ah, okay. So 4 forces. And the big dream is unifying them.
The ultimate goal. A single theory where these 4 are just different faces of one thing. Physicists have tried unifying strong, weak, and EM forces into grand unified theories, GUTs.
Have they managed it?
Partially. GUTs suggest that at incredibly high energies, way beyond our current accelerators, think solar system sized, these 3 forces merge, become comparable in strength.
Like different phases of matter. Water, ice, steam.
Kind of like that. GUTs make some predictions we can test, though. One is proton decay.
Protons aren't stable forever. We're made of them.
Well, the predicted lifetime is incredibly long. Experiments haven't seen any decay yet, which rules out the simplest GUTs, but not necessarily more complex ones. The lower limit is already vastly older than the universe.
Any other predictions?
Yes, a really interesting one about why there's more matter than antimatter in the universe.
Because the Big Bang should have made equal amounts, right? Which would have just annihilated.
Exactly. We wouldn't be here. GUTs predict that in the very hot early universe, certain processes could have created a tiny, tiny excess of quarks over antiquarks. Like maybe 1 extra quark for every billion quark-antiquark pairs.
And that tiny bit left over is everything.
That's the idea.
Yeah.
So our existence is actually kind of a circumstantial evidence for GUT-like physics, even if the details aren't nailed down.
Okay, so GUTs try for 3 forces, But gravity's still the odd one out.
That's the biggest hurdle. Merging general relativity, our theory of gravity on the large scale, with quantum mechanics, our theory of the small, quantum gravity.
Why is it so hard?
Because when you try to combine them, you get infinities. Nonsense answers.
Where do infinities come from?
Quantum uncertainty says even empty space is fizzing with virtual particle-antiparticle pairs popping in and out of existence. These have energy, which means mass. Easy MC. Add up the gravity of all these virtual particles. Infinite mass energy, curving space, infinitely everywhere.
Which is clearly not happening.
Right. For the other forces, there's a mathematical trick called renormalization, basically subtracting infinities to get sensible answers. It works, but it feels a bit sketchy. And it doesn't seem to work properly for gravity.
Is this where string theory enters the picture?
String theory is a major contender. It says fundamental particles aren't points, but tiny vibrating strings. Different vibrations, different particles. And crucially, one vibration mode looks just like the graviton, the gravity particle.
But it needs extra dimensions.
Often, yes. Extra spatial dimensions, curled up incredibly small so we don't see them. The source mentions this idea that maybe life like ours can only exist where there's one time and three big space dimensions, a nod to the anthropic principle.
So string theory might work, but it's complex and not yet proven.
Still very much a work in progress. The quest continues. Okay, let's bring GR and QM together in a different way, black holes, which, as you hinted, might not be totally black.
Formed when massive stars collapse, right?
If they're heavy enough, yeah. Above the Chandrasekhar limit, electron pressure fails. Above maybe 1.5 to 2 solar masses, neutron pressure fails too. Collapse continues to a singularity.
Leaving behind the event horizon, the point of no return.
Right, the boundary where gravity is so strong, even light can't escape. Its definition is based on those light rays just trying to get out but getting stuck.
You had a realization about that definition late one night.
Huh, yes, the source mentions that. November 1970, after my daughter was born. Suddenly seemed clear that defining it by the boundary of light escape paths was the right way.
But if nothing escapes, how do we even know they're there?
Indirectly. We see their gravity affecting things nearby. Stars orbiting something invisible but massive, gas swirling in super fast, getting heated up, emitting X-rays, light being bent.
The Hubble telescope saw that disk in M87, rotating around something billions of times the sun's mass.
Exactly. Has to be a supermassive black hole. And then there are gravitational waves.
Ripples in space-time from accelerating masses, like merging black holes.
Yes. Einstein predicted them. The Hulse-Taylor binary pulsar provided amazing indirect evidence it lost energy exactly as GR predicted via gravitational waves. That got a Nobel.
And then LIGO detected them directly in 2016.
A huge moment. Hearing the chirp of two black holes merging billions of light years away opened a whole new way to see the universe. Confirmed black holes exist and merge.
Okay, so classical black holes are real, but ain't so black. Quantum effects.
That's where it gets interesting. In the early 70s, talking with Soviet physicists like Zeldovich and Starobinsky, they suggested quantum effects might make rotating black holes emit particles. I thought non-rotating ones wouldn't.
Yeah.
But then I did the calculation. And to my surprise, maybe even annoyance, I found they should emit particles.
Full annoyance.
Well, partly because it seemed to back up Jacob Bekenstein's idea that black holes have entropy related to their surface area. Classically, throwing entropy into a black hole seemed to violate the second law of thermodynamics. Total disorder should always increase. Bekenstein said the black hole's area increase counts as entropy. I was skeptical at first.
But your calculations showed they radiate, like a hot object.
Exactly like a hot body, with a temperature that's inversely proportional to their mass. Smaller black holes are hotter. This is Hawking radiation.
So they leak energy and mass.
Yes, positive energy particles escape, balanced by negative energy flowing in. Negative energy reduces mass, EMC soy way. So the black hole slowly shrinks. And the entropy of the radiation it emits is more than the entropy lost by the black hole shrinking, saving the second law.
So black holes aren't eternal, they evaporate.
Eventually, yes. For stellar mass black holes, the time is incredibly long, way longer than the current age of the universe. But what about primordial black holes?
PPHBs. Formed in the early universe, not from stars. Could be much smaller.
Potentially, yes. If density fluctuations were big enough back then, a PHB with the mass of a mountain would be tiny, nucleosized. And because it's low mass, it would be much hotter and radiating much faster.
Could they be evaporating now, maybe exploding?
A PHB starting with about 1 billion tons would have a lifetime about the age of the universe. So ones around that mass could be finishing their evaporation right now. Smaller ones are gone already. Bigger ones are still radiating X-rays and gamma rays. The final moments would be a huge burst of energy.
Thousands of megawatts. Could we see that?
It's tough. There's a gamma ray background we don't fully understand. We also see gamma ray bursts, GRBs. Detecting an exploding PHB nearby would be hard, statistically unlikely.
Are GRBs exploding PHBs?
It's one possibility, but maybe less favored now. Colliding neutron stars are a very strong candidate, especially since we've seen gravitational waves from those events matching GRB locations. LIGO helps sort this out.
Still, Hawking radiation itself was a massive theoretical step, wasn't it? Using both GR and QM.
It was the first really solid prediction that relied intrinsically on both theories.
Mm.
There was definitely skepticism initially. One prominent physicist called it nonsense at a conference. But the calculations held up, others confirmed it, and it's now widely accepted.
Does it change the idea that falling in is a one-way trip?
Sort of. The energy eventually comes back out as radiation. So it's recycled, in a way. But it's not like the astronaut reappears. They'd be torn apart long before reaching the classical singularity. And the outgoing radiation is random, thermal. It doesn't carry the information about what fell in.
So energy returned, but identity lost. Does radiation suggest QM might fix the singularity inside the black hole too?
It hints that way. If the black hole completely evaporates, the singularity must vanish. It strongly suggests a full quantum gravity theory would smooth out that infinite point.
Which brings us back to the Big Bang singularity. Can quantum gravity tell us about the start of the universe?
It offers a completely different picture. One approach uses Feynman's sum over histories.
Where a particle takes all possible paths simultaneously?
Right. Applied to the whole universe, you sum over all possible space-time histories. To make the math work, you often use imaginary time.
Imaginary time. Okay, that sounds abstract.
It's a mathematical tool. You treat the time coordinate like it's another space coordinate. The distinction blurs.
Why do that? How does it help with the beginning?
In imaginary time, you can propose the no boundary condition.
The universe has no edge or boundary in imaginary time.
That's the idea. Like the surface of a sphere, finite, but no edge, no starting point where laws break down, no initial singularity is needed. The universe just is.
So in this imaginary time picture, there's no Big Bang singularity moment.
Not in the same way as classical GR implies. When you translate back to real time, you might still get something that looks like a Big Bang start, but the underlying quantum description is smooth, boundaryless.
So your earlier work showed singularities must exist in GR, but this later quantum idea suggests they might be removed at a deeper level.
Exactly. The theorems show where GR breaks down and QM must come in. The no-boundary proposal is one way quantum gravity might resolve that breakdown at the ultimate beginning.
Does the no-boundary idea predict anything we can test?
It predicts the universe should have started in a very smooth, ordered state, with just the minimum possible fluctuations allowed by the uncertainty principle. Then, a period of inflation happened.
Super rapid expansion right at the beginning.
Yes, exponential expansion for a fraction of a second. This blew up those tiny quantum fluctuations to cosmic scales. They became the seeds for galaxy formation.
And the pattern of those fluctuations matches the ripples seen in the CMB.
Remarkably well. The combination of quantum fluctuations from the no-boundary condition plus inflation gives a pattern of structure that looks very much like what COBE and later missions observed in the CMB.
So quantum fuzziness at the start, amplified by inflation, created everything. That's mind-blowing.
It connects the tiniest scales to the largest. Okay, thinking about beginnings and ends, what about the arrow of time? Why does time only seem to go one way for us?
Right. We remember the past, not the future. Things break, they don't unbreak.
There seem to be three arrows pointing the same way.
Thermodynamic. Disorder increases.
Yes, entropy.
Yeah.
Second law. Far more ways for things to be disordered than ordered. Scrambled eggs don't unscramble.
Psychological.
Print-
Our memory works forwards.
Check. And cosmological. The universe is expanding.
And they all line up. Why?
Classical GR allows expansion or contraction, doesn't dictate a direction or explain increasing disorder. But quantum gravity with the no-boundary condition suggests the universe had to start in a highly ordered, smooth state. That initial order is what sets the thermodynamic arrow, which likely drives the psychological arrow, all happening within the expanding cosmological context.
Speaking of time travel, is that on the table at all?
The sci-fi dream. Relativity's speed limit makes interstellar travel tough. Alpha Centauri is 4 light-years away, minimum 8-year round trip just to send a signal.
Galaxy center, 100,000 light years. Forget popping over.
Pretty much. The twins paradox helps the traveler. They age less, but they come back to a vastly different future.
Mhm.
But if you could beat the speed of light,
Relativity says you could go back in time. That limerick.
there was a young lady of white.
Yep. Faster than light travel and backward time travel seem linked in relativity.
So how could you theoretically do it? Warp drive, wormholes.
You'd need to seriously warp space-time. Create shortcuts, like wormholes connecting distant points or times.
Is there any physics suggesting that's even possible? Extreme warping.
Well, we know gravity warps space-time, and things like the Casimir effect, where two metal plates in a vacuum attract, show that negative energy density, which seems necessary to stabilize wormholes or warp drives, might be physically possible.
So, maybe. But then the paradoxes kick in.
The grandfather paradox being the classic. Go back, stop your grandfather meeting your grandmother. Poof, you don't exist to go back. How does history stay consistent?
Yeah, how does physics handle that? Two main ideas mentioned in the source. One is consistent histories. Maybe you can go back, but you can't change anything that would lead to a paradox. Your actions were always part of history. Maybe free will is constrained in those situations.
Or maybe you just can't do it.
That's the other idea, my chronology protection conjecture. The idea that the laws of physics themselves prevent macroscopic time travel.
How? What stops you?
One possibility involves those virtual particles again. If you create a time loop warp, virtual particles could loop around, become real, and build up infinite energy density right at the warp.
Like a feedback loop that destroys the time machine before it works?
Effectively, yes.
Yeah.
The infinite energy would curve space-time so much it prevents the stable warp needed. It's plausible, but not rigorously proven it would always happen. So the door isn't completely shut, theoretically. But
where are all the tourists from the future?
My question exactly. Maybe they're very discreet. Maybe they're UFOs. Or maybe, as the conjecture suggests, it's just not possible. I tend towards the latter.
What an incredible sweep of ideas. From crystal spheres to quantum foam, curved space-time radiating black holes. Where does this search finally lead?
To the ultimate prize. A complete unified theory. One framework merging GR, QM, all four forces. Our current theories, GUTs, etc., are powerful but incomplete. They don't include gravity, or they need tweaking.
A single set of rules explaining everything. All the constants, particle masses.
That's the dream. Though the source raises an interesting point. Maybe it's not one single equation, but more like a set of overlapping maps needed to describe the whole surface of reality, like you need multiple maps for the Earth. Gödel's theorem about arithmetic maybe hints we can't derive everything from one finite set of axioms.
If we did find such a theory, what would change?
We could never be 100% sure it's the final word. Science always allows for surprises. But if it was consistent and matched all observations, we'd have incredible confidence.
It would be the end of a search thousands of years old.
It would. And the impact, huge. Science is so specialized now. But a truly fundamental theory, once understood, could potentially be simplified, taught widely.
So everyone could grasp the basic rules of the universe and our place in it.
That's the hope. Imagine millions understanding the basics, like they grasp curved space-time now, which was once understood by only a handful. It would change our whole perspective.
And it loops back to determinism. QM seemed to kill Laplace's clockwork universe with randomness.
Yes, but the source adds a final twist. Maybe the randomness isn't fundamental. Maybe it comes from us trying to impose particle ideas, position, velocity, onto an underlying reality that is purely wave-like and evolved deterministically according to something like the Schrödinger equation.
So the uncertainty is in our measurement trying to force a wave into a particle box, not in the wave itself.
It's a deep thought. Maybe the underlying laws are deterministic, but our interaction with them introduces the probabilities we see.
Wow. What a journey, exploring the universe through the lens of a brief history of time. From solid Earth to expanding space-time, quantum fuzziness, black holes that aren't quite black, the nature of time itself, and this ongoing quest for unification.
It really showcases human ingenuity, doesn't it? How far we've come in figuring things out. Driven by curiosity and observation, our understanding is constantly evolving, never static.
It's humbling and inspiring, the scale of the questions and the incredible thinking needed to even approach them.
It truly is.
Okay, as we wrap up, here's one last thing for you to chew on. If quantum gravity, maybe through something like the no-boundary idea, paints a picture of a universe that, in imaginary time, just has no beginning, no end, and if the fundamental laws determine how it evolves, does that sneak determinism back in, even with quantum uncertainty? Maybe a subtler form than Laplace imagined. If the universe's state is fundamentally determined by the laws, what room is left for actual chance? Or even for our own choices in the grand cosmic story?